In your high school physics course, you may have come across this definition of pressure, that it is force divided by area. However, this definition fails to fully describe pressure because it only works with macroscopic fluids. In the microscopic world of kinetic theory, where gases aren't uniform like we usually see them, but are made of tiny particles, we need a different definition. To see this, we must first begin a derivation from kinetic theory that finds the average kinetic energy of gas molecules. In the end, the equation K average is 1.5 kT appears, which shows us that only temperature determines the energy within an ideal gas. To start this proof, we first look at one particle hitting one wall of a container of gas. Newton's second law tells us F equals ma. In other words, the force the particle applies to the wall equals its mass multiplied by its change in velocity and divided by the time of wall contact. We assume the particle bounces back with the same speed as before, so the total change in velocity is twice the original. Great, but now we need to find how long the particle was touching the wall. It turns out that we can't determine this. There is no way to derive it from the particle's attributes. So how do we finish the proof? Most online derivations will instead use the time it takes for the particle to hit the wall, go to the other end of the container, bounce back, and return to the wall. This period dramatically differs from the contact time, yet it still leads to the same equation in the end. How is this possible? By breaking Newton's second law, you've arrived at a truth about kinetic gases. In the end, we find that force doesn't need to change, pressure does. To see why, consider this example. A gas made up of one molecule sits in a cubic container. The gas has a certain temperature, which means our one particle has a certain velocity and hits the wall with a certain force dependent upon that speed. If we consider one wall, say the right one, and measure the pressure on it in the usual sense, we find its value to be the particle's force of impact divided by the wall's area. Now, we double the length of the box, keeping the right side's area constant. As a result, the box's volume doubles. We also assume the process is isothermal in that it keeps temperature constant, so the particle's velocity and force of impact are also the same. According to the ideal gas law, if the temperature stays the same and the volume doubles, the pressure must halve. However, the old definition of pressure tells us otherwise. The force of impact and the area of the wall are still the same, so the pressure must be constant as well. So what changed? It turns out that the frequency of impact did. Since the particle now has to go double the distance to return to the right wall, it hits that wall half as often. Thus, pressure has a time-dependent nature. Using calculus, we can fix the definition by replacing force with a continuous average of the force. Essentially, we take the average of all forces over a certain amount of time and see what the average tends to as the time period grows. We then divide by area and voila, pressure. We can now use this definition to derive the average kinetic energy of a gas. First, let's plot the force on the right wall as a function of time. You can see that there are periodic blips, which represent the particle hitting the wall, flying off to the opposite wall, rebounding, and then returning to strike the right side once again. F is the average force of contact, the height of the blips. Delta T is the time of contact, the width of the blips, and tau is the period of this cycle, the time between the blips. Here, our average force over time is the same as the average force over one cycle. To calculate this, we find the area under one cycle of the curve, which is the area of one blip, F times delta T. We then divide this quantity by the duration of one cycle, tau. Now, we just divide by the area of the right wall, and we have the pressure one particle exerts on our right wall. But what is F in this equation? It turns out that we derive it with Newton's second laws before. So for one particle, F is 2mv over delta T. When we plug this into the pressure of one particle, the delta T's cancel and tau takes its place. The substitution works. Thermodynamics lives on. So what about the old definition of pressure? Well, if you have a ton of particles, billions and billions, you can see that the force versus time graph becomes essentially a flat line. Thus, our continuous average of the force and the actual force are equal, and the original definition of pressure works on a macroscopic scale. If you want to see the proof of the equation K average is 1.5 kT, or learn more about kinetic theory, there are plenty of videos and resources online, but just remember, when they use tau instead of T, give them one more chance. They're under pressure.